Bubble sort is one of the simplest algorithms, and it can provide a great foundation for understanding how algorithms work in general and how they can be optimized. Even though it's far from being the fastest sorting algorithm, it's a great place to start, and many universities include it in their curriculum specifically for that reason. So having the initial array, we want to sort it in increasing order. The core idea behind the bubble sort algorithm is just a single operation. As we go through the array, as soon as we notice neighbor elements that are not ordered properly, we swap their places. So if the current element is larger than the next one, we change their places, bringing the smaller one to the left while pushing the larger one to the right. So given the initial unsorted array, we look at the first two elements of the array, and if they are not placed in increasing order, we swap them. We then move to the next pair, and if they are not ordered properly, we swap their places. This process is repeated until we reach the end of the list, and after that we go back to the very first two elements of the array and repeat this whole process again. We look at the first pair in the array and compare them. If they are not in order, we swap them, otherwise we don't touch them. Then we move on to the next pair, then to the one after those, and repeat it until we reach the end of the array. That way, on each iteration, the largest element will bubble up to the right part of the array, finding its correct and final place. This is exactly why this algorithm was named bubble sort. You can think of each number as a bubble where the size of the bubble matches the number, so the smaller numbers can be drawn as smaller bubbles and larger ones as larger bubbles. After looking through the list of bubbles for the first time, the largest bubble will appear at the very end of the array. On the next iteration, the second largest bubble will bubble up and appear next to it. After several iterations, all the bubbles will find their correct places and the whole array will be properly sorted. We represent each number as a bubble for aesthetic purposes to better illustrate the intuition behind the name of the algorithm. There is no functional utility behind it, and we could have easily explained the algorithm using array cells instead of bubbles. But I guess this makes the process a bit more memorable and intuitive. Let's go over the algorithm in more detail, after which we will try to implement it. We first look at the first two elements of the array, and if they are not placed in increasing order, we swap them. After which we move to the next pair of elements. If they are not placed correctly, we swap their places. We then move to the next pair and repeat this process until reaching the end of the list. This way, the largest element will bubble up to the very end of the array. So we go back to the start of the array and repeat this whole process. We compare the first element to the second one. If those two are not placed correctly, we swap them, otherwise we leave them in their places. After which we move to the next pair and repeat the process of swapping elements if they are not placed correctly until reaching the end of the list. This way, the second largest element will bubble up and appear in its correct place right next to the largest element. Notice that we have already placed at least two elements in their correct positions. Great, we go back again to the start of the array and repeat the process. We will compare the neighbor elements and swap them if they are not placed in the right order. This way we will know for sure that the third largest element will appear next to the second largest element. Notice that we were lucky here and the fourth largest element got to its right place. But we won't change anything about our strategy and will continue the process. On the next iteration, we would compare the first pair of elements, then the next pair, and swap the ones that are not in order until reaching the end of the array. With our array, we're actually ahead of the worst case scenario and already have most of the array sorted, but this doesn't happen every time. On the next iteration, we will go back to the start of the array and we'll repeat the whole process again. Notice that we have already sorted the whole array. We can go over the array one more time just to make sure that everything is in increasing order. You've probably noticed by now that on each iteration, the next largest element bubbles up and finds its correct place. As there are n numbers in the array, we have to perform at most n-1 loops to place the corresponding largest element in its place. So during the first loop, we place the largest element in its place. During the second loop, we place the second largest element in its place. On the third one, the third largest element finds its place. And that process repeats until all the elements find their correct places. Having this, we can conclude that we need to perform at most n-1 loops to place all the elements from largest to smallest in their places. This information is already sufficient to implement the algorithm and even perform several optimizations. You can even pause the video now and try to implement the algorithm yourself. Okay, as we saw that we need to perform at most n-1 loops to place the largest element in their places, we would loop from 0 up to the length of the array -1. We would then loop through all the numbers to compare the neighbor elements. As we compare the current element to the next one, we will loop up to the length of the array -1 instead of the length of the array to ensure we don't go over the array when performing the comparison. We will then compare the current element to the next one, And if they're not placed in increasing order, meaning if the current one is larger than the next one, we will swap them. This way, we will have the most straightforward implementation of the bubble sort algorithm. But you've probably noticed that there are several optimizations that we can do to improve the algorithm and make sure we don't do too many redundant operations. The first one is the fact that on each iteration, the corresponding largest element bubbles up to its correct place. So there is absolutely no need to touch that element and all the elements larger, as they're already in their correct positions. So instead of looping all the way to the end of the list, we can loop up to the place where some elements might not be in their correct positions. So we will update the outer loop to point to the upper bound, beyond which there is no need to loop through. So on the first iteration, that would be the last index. On the next iteration, it would be the second last. On the third, it would be the third last, and so on. So the outer loop would be updated to start from the last index and go up to 0 by decreasing the upper bound by 1 on each iteration. For the inner loop, instead of going up to the end of the array, we would go up to the upper bound defined by the outer loop. This would improve the algorithm a little, and we will avoid performing some redundant operations. But as we saw with our example, we might be able to sort the array faster than expected. What if most of the largest elements are already in their correct places when we start running the bubble sort algorithm? Well, in that case, we might go over the array many times without changing it at all. So we can introduce another optimization and track if we have changed the array, because if we haven't changed anything during the inner loop, then the array is already sorted and we can stop the algorithm. So we can introduce a boolean variable change to track if we have changed the array when going through it in our inner loop. If we swap two neighbors, we will set the value of change to true to indicate that the inner loop modified the array and the array isn't sorted yet. After that, we will check if there were any changes made to the array by the inner loop. If there were no changes, we can break the loop and stop the algorithm. This way, we will stop the algorithm as soon as we perform one inner loop that didn't modify the array at all. Okay, let's see the algorithm in action and look at how our implementation would work for this array. We will initialize the upper bound to be the length of the array minus 1. Initially, the change flag would be false and we would enter the inner for loop. We will start from I equals to 0 and check if the array element at index 0 is larger than the element at index 1. As 12 is larger than 3, we will enter the if block, swap the elements, and set the change flag to true. We will then check if the array element at index 1 is larger than the element at index 2. As 12 is larger than 5, we will enter the if block again, swap the elements, and set the change flag to true. After that, we will compare the element at index 2 to the one at index 3. As 12 is larger than 9, we will swap them and set change to true. In the next iteration, we will compare 12 and 4. As 12 is larger, we will swap their places again. After which, we will compare 12 and 1. As 12 is larger, we will enter the if block again. Finally, we will compare 12 to the last element of the array, which is 7. And as 12 is larger, we will swap them. This will ensure that 12, which is the largest element in the array, is in its correct place. Now, as the value of change is true, we won't break the loop. We will go back to the very start of the loop and set the value of the upper bound to 5. We will initialize the change flag to false and enter the for loop. Starting from the first pair, we will compare the value at index 0 to the value at index 1. As 3 is not larger than 5, we won't enter the if block. After that, we will look at the values at index 1 and 2 and compare them. As 5 is not larger than 9, we won't enter the if block again. We will then compare 9 and 4, and as 9 is larger than 4, we will swap them and set the value of change to true. During the next iteration, we will compare 9 and 1. As 9 is larger than 1, we will swap them again. After that, we will compare 9 and 7. As they are not in the right order, we will swap them, and that way 9 will appear in its final place. As we have changed the array, we won't break the loop and will continue iterating by going to the start of the outer loop and decreasing the value of the upper bound by 1. We will set the value of change to false and enter the inner for loop. We will start by comparing 3 to 5, and as 3 is not greater than 5, we won't enter the if block. In the next iteration, we will compare 5 and 4. As 5 is larger than 4, we will enter the if block and swap those two values, as well as set the value of change to true. After that, we will compare 5 and 1. As 5 is greater than 1, we will swap them. In the next step, we will compare 5 and 7. As 5 is not greater than 7, we won't do anything. As we change the array during this iteration, we won't break the loop again, and we'll continue the process by going to the next value of the upper bound. The value of change will reset to false again, and we will start the inner loop. We will compare 3 and 4. As they are ordered correctly, we won't enter the if block. We will then compare 4 and 1. As 4 is greater than 1, we will swap those values and set change to true. After that, we will compare 4 and 5. As 4 is not larger than 5, we won't enter the if block. When checking the value of changed, we will see that it's set to true as we modified the array on this iteration as well, so we won't stop the loop. Moving forward, we will decrease the value of the upper bound again and enter the for loop. We will reset the value of changed and we'll enter the inner loop again. We will compare the values at indices 0 and 1, and as 3 is greater than 1, we will enter the if block and swap the values while also setting the value of changed to true. After that, we will compare 3 and 4, and as they are ordered correctly, we won't do anything. We will then check if the array was changed, and as it was changed, we won't stop the loop. We will move forward and decrease the value of the upper bound again. Entering the loop, we will set the value of change to false and enter the inner loop. We will compare the value at index 0 to the value at index 1. As 1 is smaller than 3, we won't enter the if block. After that, we will check if the value of changed is false. As we didn't perform any swaps, the value of changed is still set to false, and by entering the if block, we break the loop and stop the algorithm. So after all these iterations, we finally have a sorted array where on each iteration, the larger values kept bubbling up, finding the correct places in the array. This is great, but what would happen if some elements of the initial array had equal values? It's clear that the algorithm would still work correctly, but a more interesting question is, would they still preserve their relative order? So, if there are several elements with equal values, would the final array have them in the same initial order, or would their order be changed when performing the bubble sort algorithm? Many sorting algorithms like heap sort or radix sort don't guarantee preserving the initial order of equal elements. Other algorithms like merge sort or insertion sort, on the other hand, preserve the initial order. The algorithms that preserve the initial order of equal elements are called stable. So merge sort, for instance, is stable. But what about bubble sort? Well, let's run the bubble sort algorithm on this array to see if any of the 7s change their order. The upper bound would start from the array length -1. We will initialize the change flag with false and enter the inner loop. We would compare the first 2 elements. As 12 is larger than 7, we will swap them. On the next iteration, we will swap 12 and 5, then 12 and 7, after which we will swap 12 and the next 7, then 12 and 1, and finally, we will swap 12 with the last 7, placing 12 at the very end of the array. We will go back to the start of the array and compare the first pair. As 7 is greater than 5, we will swap them. After that, we will compare 7 and 7. As 7 is not greater than 7, we won't do anything. So the initial order of 2 7s won't change. We will move on to compare the next pair of 7s. As they're equal to each other, we won't enter the if block and their order won't be changed. We will then move on to compare 7 and 1, and as 7 is greater, we will swap their places. During the next step, we will compare the 2 7s again. As none of them is greater than the other, we won't touch them and they will preserve their initial order. You can notice that no matter how many iterations we perform on the initial array, the initial order of equal elements doesn't change. As we only swap elements if the current element is strictly larger than the next one, the bubble sort won't swap 2 equal elements. That ensures that bubble sort is actually stable, meaning if 2 elements have equal values, they will preserve their initial order and won't swap places. So bubble sort is a stable sorting algorithm. Another very important property of a sorting algorithm is whether it uses additional memory proportional to the given array. If it only requires constant extra memory or doesn't require any additional memory at all, we say that the algorithm performs in-place sorting. Some algorithms like counting sort or merge sort usually require additional memory and can cause issues if memory is a large constraint. If we look at the implementation of the bubble sort algorithm, we can notice that we don't use any additional memory. So bubble sort is pretty memory efficient and performs in-place sorting. That's the second property of the bubble sort algorithm. So bubble sort is stable, meaning that it doesn't change the initial order of equal values, and it also performs in-place sorting, meaning that it doesn't require additional memory proportional to the given array. We have done several optimizations and improved our implementation. Let's see what would be the overall time complexity for the bubble sort algorithm. First, let's see how many operations the algorithm would perform if the initial array is already sorted. If it's already in the correct order, the algorithm would look through all the neighbors from the start to the very end, and because no changes would occur in the array, the algorithm would stop after the first loop. So in the best case scenario, where all the elements are already sorted, the algorithm would perform all of n operations. Let's have a look at the worst case scenario. Can you construct an array that would force the bubble sort algorithm to perform as many operations as possible? You can pause the video and try to construct an array like that. Okay, so The worst case scenario actually occurs when all the elements are sorted in reverse order. That causes the outer loop to go from the length of the array -1 up to 0, while the inner loop goes from 0 to the upper bound on each iteration and swaps the neighbor elements every time. So on the first iteration of the outer loop, there will be n-1 comparisons and swaps. On the second one, there will be n-2 comparisons and swaps, and so on, until there is only a single comparison and swap. So in total, there will be n-1 plus n-2 plus n-3, etc. up to 1 operations. And if we sum all of these numbers that form an arithmetic progression where the first number is n-1 and the last one is 1, with a difference of -1 between all the neighbors, we will get n times n-1 divided by 2, or n squared minus n divided by 2, which expressed with a big O notation would be O of n squared. So in the worst case, the algorithm performs O of n squared operations. On average, if the array is randomly shuffled, the outer loop of the bubble sort might require n divided by 2 passes. The inner loop would still perform O of n operations for each of those passes, so the total time complexity on average would still be O of n squared. This makes the bubble sort algorithm one of the slowest sorting algorithms out there. We will explore some more efficient sorting algorithms in the future. By the way, have a look at the best case and the worst case scenarios again. Can you modify the algorithm to sort in decreasing order to turn the worst case scenario into the best and the best case scenario into the worst? If you'd like to practice the bubble sort algorithm and try your hand at other sorting techniques, you can head to Profound Academy after clicking the like button and implement these algorithms in your favorite programming language. I'll leave the link in the description below. Don't forget to subscribe to see more tutorials like this. Thanks for watching, and I will see you in the next one.